Here is a voltage drop question from the Canadian Electrical Code, Section 8, or it pertains to the Canadian Electrical Code, Section 8, which is about voltage drop. In this problem, this is a little bit of a non-conventional problem. It's a little bit harder than most problems about voltage drop from Section 8, so it's a really good one to study. Here we're saying if a number 14 wire carrying 10 amps at 1% voltage drop and 120 volts can be 6.1 meters long, so this is known, then use that information to figure out how long could the same conductor be in a 600 volt circuit. So I'm looking for the length in meters of this conductor. So I know about this other conductor. How long can the same conductor be in a 600 volt circuit? Well, what I would do is I would look at this known conductor first. And I think it's really important to know that when you're doing the voltage drop calculations, it's all the same equation. So I don't even want to write the equation in a different way. I like writing the equation like this. It's 1,000 meters per kilometers because that deals with our units, our length units, and our K units, our K factor units. V drop. And if you don't know this equation, then make sure that you review my videos where I talk about what this equation is that basically summarizes everything about voltage drop. Everything can be calculated from this one equation if you decide to write it like this. I in amps times length in meters. So if you don't know this equation, because it's not really specified in the book like this, but this is the equation that will let you solve absolutely everything. And we know, in this case, we know the length, 6.1 meters, if the current is 10 amps. Of course, we know F, because that's going to be 2, and we know the voltage drop is 1%. Then we can solve for the K factor. So we can find from here, we can find the K factor that contributed to that 6.1 meter. And then we can use that same K factor because it's the same conductor in figuring what it would be in a 600 volt circuit. From here, we can find K for this conductor. And K tells me this conductor can handle a certain amount of ohms per meter, right? The K factor is ohms per meter. So this conductor can do this many ohms per meter in this circuit. It should be able to do that many ohms per meter in the 600 volt circuit as well. So from here, we can find K for this conductor, then use it in the 600 volt circuit. All right, so let's do that. Let's find K. So I'm going to use this equation and I'm going to rearrange to solve for K. K factor 3. All right, and if you don't know what I'm talking about there, about this equation, again, look at my video where I develop this equation based on Section 8 of the code book and Table D3. All right, so I'm just rearranging this equation. I'm isolating K factor by moving everything else to the other side. What I'm going to do is basically take all of this content and divide it through to the other side, which puts it on this side, and then I'll stick to the right of the equal sign. So here I am doing that. And you'll have to rewind this video if you don't understand what I mean by rearranging this equation. Or comment below and ask me any questions about this, why I'm doing this or how I'm doing this. Not everybody has the same math background. I believe I put KK up here instead of kilometers. This voltage drop of 1.2 I just put in here is because I wanted 1% voltage drop of 120. So V drop equals 120 volts times 1%. And that's where I got 1.2 volts for the voltage drop that I just subbed in right here. And again, comment below if you have any other questions. So F from the note 2. This is from note 2. This is note 2. F from note 2 is 2. If I go into table D3 note 2, I'll get 2. Current in this question, it said it was 10.0 amps. I'm saying 0.0 to have appropriate significant digits. 6.1, really that should be 6.10 if I'm talking about significant digits, but that could be another video for another time. We can talk about significant digits. This gives me 1200 over 122 if I type that into my calculator. Meters and meters cancel out. No, meters. Yes, meters and meters cancel. Wait. Let me see, meters and meters are canceling out. Volt over amps. So I'm going to get ohms per kilometer. Yes, and that's what I want. So kilometer, I'm going to have a kilometer in the denominator. I'm going to volt here. I'll just do it. It's going to be volts per amp. And we know from V equals IR, that voltage is amps times resistance. So volt over amps is ohms. So volt over amps and then kilometer is in the denominator. So that works out to 9.8. Turn the volts over amps into ohms per kilometer. There we go. Ohms per kilometer. All right. Now, it's worthwhile to note that that's a K that is derated. So let's figure out what the note 2 value would be in this case. So we have this derated value. It's K is derated by factor 3 is 9.8. So K derated is 9.8 ohms per kilometer. And that is the K that is the table 3 value. That's what I actually choose from the table. And the note 2 value then, because the derated K is the K from the table times the note 2 value, then that would be 9.8 over 10.2. Therefore, the note 2 value is 9.6. So what we must use is the derated value. Therefore, we must use derated value, which is 9.8 ohms per kilometer. So what I'm saying here is when you look at table D3, you're going to see 10.2. And so here sits 10.2 in the table, but you would never put 10.2 into your equation. So now that we're going to solve for the 600 volt circuit, I'm not going to factor in straight from the table into the 600 volt circuit equation K factor because we always use a derated K factor. So we have to use this derated one, not what was in the table. So if 9.6 was our derating factor, our note 2 value, then 10.2 is what would sit in the table. 9.8 is what's derated, so that's what we should use in our equation. All right, so we just took our known wire conductor condition, we solved for K. Now we'll use K to sub into the new circuit. So a little bit of a tricky question. Now we can use K to sub into new circuit. All right, here we go. So we'll use this same equation. 1,000 meters per kilometer. Comment below if you don't know where this equation comes from, or look at my other video where I show you where this equation comes from. So our K is going to be already derated. It's going to be 9.81. F of note 2, I in amps, and length in meters. And here we are asking the question, well, what would the new length be for the new voltage? So let me solve for length. Let me know below if you don't know how to solve for length, because that shouldn't be holding you back. Length, I'm going to divide all of this through to the other side of the equation, switch where it is on the equal sign, so I get 1,000 times voltage drop. I recommend you always carry your units. Your units tell you if you've done anything right or wrong. If you come up with the wrong units, you've just done an error in your algebra, most likely. All right, now we can substitute in our values and we're going to get the length. The new voltage drop is going to be 600 volts times the voltage drop of 0.01. That's a 1% voltage drop. So that's going to be 6 volts there. The K factor is 9.81. All right. And then times that by 2, which is it's F of note 2, times 10 amps. Oops. And that is going to be, if I substitute all of that in, I'm going to get 6,000 on the numerator here. Meters going to change, going to cross out with meters. We're going to have volts over amps and kilometers in the denominator. So volts over amps times 1 over kilometers. From my calculator, I have 196 here. I'm going to divide through 6,000 divided by 196. I'm going to get 30.6. I did something wrong. I have volts, I have amps, and I have ohms in the denominator there. There we go. Let me put that ohms in the denominator. Ohms in the denominator, not the numerator. It's in the numerator of this denominator, which means it's in the denominator here. Volts times amps, volts divided by amps times ohms, which means that this is actually a volt over an amp times 1 over ohms times 1 over kilometer. And a volt over an amp, of course, is an ohm times 1 over ohm times 1 over kilometer. 9.81 is in ohms per kilometer. There we go. Oh, it's on ohms per kilometer. So it did not cross out with meter. It did not cross out with meter. Excuse my units here. Of course, units are very important because they tell us if we've done things right or wrong, and I thought I just did something wrong because of that. So kilometers cross out. Kilometer crosses out with this kilometer. We're left with meter. Excuse this. This is actually a meter. Nope. It's not in a denominator. It's in a numerator up here. Meter is sitting in numerator up here. Therefore, it's in a numerator up here. Excuse my math. And then I'm going to multiply it by the meter here. Meter over 1, meter over 1. Ohms are canceling out. Now I am a happier person because this ends up being meters. Meters. There we go. So the new length of this same conductor used in a 600-volt circuit will be 30.6 meters. Let's summarize that question type again. That question says that we have a conductor that's number 14 wire carrying 10 amps at 1% voltage drop and 120 volts. It can be 6.1 meters long. How long could it be in 600-volt circuit? We solved for K, and then we decided it could be 30.6 meters long in a 600-volt circuit. And that's how you do that type of question. It's a little bit long, a little bit involved, takes a lot of time. Don't forget to remember that that K factor has to be a derated factor, not one just from the table. Hopefully that's helpful to you. If you like these videos, then please subscribe, hit like, and put a comment below what's good about them, what's bad about them, and what else do you need to know. Thank you so much.